All right. I reset the audio. Can you guys on Zoom hear us?
Yes, thank you.
All right. Sorry about that. It,
Okay,
it was configured right. I just ended up turning everything
restarting
off
it.
and back on.
Okay. All right. Back from the top, I guess. So chapter 6, decision trees. Here's the various concepts that we'll be walking through. I just started talking about training the trees. So they gave us this beginner snippet of code, and so this is what we'll be digging into more throughout the chapter. And so for now, just here's 5, 6 lines of code, and don't worry too much about the details behind it, but um, we start with this loading the iris data set. So this is a data set saying here's the length and width of some petals, and then we want to classify what kind of flower it is based on that. So we have the data set, and then after that, we have the scikit-learn implementation of decision tree classifier. And then what this is going to do is it's going to try to make a decision tree for us that classifies the petals in various different ways. So we train it and then we get this visualization out. So this visualization is showing the decision tree that gets made by this process. And so we can look at this and understand the various different pieces of it. So this top piece is called the root node. So this is the beginning of everything. This is the first decision that's made. And we can look at this and read into it a little bit, and we'll learn more about all the details of this little bubble later on. So we say if the petal length is less than or equal to 2.45, then go to this branch. If it's not, then go to that branch. And so that's just the gist of a decision tree. You're making a whole bunch of different splits, and then you're saying go down this path or go down that path. Um, and so one of the measures we're going to learn about is Gini impurity. So this is saying that the Gini impurity is 0.667 there, so it's not very pure at that point. And then all the way at the leaf nodes where it actually terminates, it makes a final decision. It's saying it's 0.168 or 0.043, which is much more pure. So we'll learn about that more. But in general, this is a decision tree. This is what we're building. This is the model that's learning the pattern that we're trying to teach it. Um, so with scikit-learn, it just automatically does this. The root node is the first decision. The leaf node is anywhere that it ends. So it makes a final classification saying it's this flower, that flower. A split node is anywhere where a decision is made. And then during inference, we can basically just follow along the chart and say, make this decision, make that decision. And then we get to some leaf node and we say, that's my classification. Um, so the one piece that is important here that I kind of glossed over is this Gini impurity is a measure of how well your classes are separated based on that decision, basically. So you're saying this petal length less than or equal to 2.45, how well does that separate out my two classes, basically? And so this is the way that it's formulated. So let's look at this specific equation. So this is saying 0 out of 54 raised to the second, 49 over 54 raised to the second, 5 over 54 raised to the second. That came from this bubble. So it's basically saying we went through this set of decisions and then 0 of them ended up one of the classes, 49 of them ended up the other class, 5 of them ended the other class. So if you look at that, 49 of them ending one class is pretty pure. So that's how you get your 0.168. So 5 of them ended up something else, but in general, you follow down this path and then you say only 5 of them end up the wrong classification. That's pretty good. And you can look at this one, and this one's even more pure. It's saying 45 of them end up this Virginica classification. Only one of them ended up versicolor, I believe. And so this one is very, very pure. Um, so we calculate this with this simple formula saying 1 is total impurity, 0 is total purity. And so all of these are added up or subtracted from 1 in order to get your final score. So with this, the decision tree ends up making these simple boundaries for you. So when we looked at linear regression and SVMs and the other stuff in the previous chapters, you end up with these wonky patterns sometimes if you're doing like polynomial regression or something else. But with decision trees, you end up with these very square lines. So like for this, it's saying basically anything that has a very short petal length is going to end up this one class. Anything over this petal length might be this class or that class. And then it's separated by the petal width. So we're just saying here's one cut here, here's one cut there. And then we're putting it into the different bins. I'll pause here for a second. Does anyone have any questions about the decision trees or this visualization here or Gini impurity? Yeah.
So decision trees can only make perpendicular lines for the separation between the classes.
Yeah.
Whereas the other models were able to make more complex patterns. Okay.
Yeah.
Does that mean there's going to be limitations to using decision trees around class separation?
Yeah. So decision trees have that limitation on them in that they can only make those simple perpendicular decision boundaries. But the advantage is you can have unlimited depth potentially. So in theory, the model has unlimited capacity. It could draw a little tiny box around every single individual point. So one of the things that I'll say about decision trees versus some of the other methods is decision trees are very good at interpolation tasks where it's like this is just kind of inferring in between values, whereas something like linear regression is probably better at extrapolating. Like this has no extrapolation capability. If we go over to petal length of 10, it's not continuing the trend in any way because it's just saying the boundary was all the way over at 2.5, for example.
Thank you.
Yeah. Yeah. Any other questions? Okay, online.
I had a question. Oh,
Yeah, go for it.
so I'm probably missed this in my reading, but could you explain what the value represents again? I know the samples in the class, but I missed what values those the value represents again in the example.
The value represents the counts of the various different classes. So at the top, it's saying we have 50 Setosa, 50 Versicolor, 50 Virginica. So it's saying at this point, we have all of the data. We have 150 data points and it's evenly distributed across our three different classes. And so at the different levels, it's saying how many remain of the different classes. So like this one is saying with this simple split, we've split out all of the Setosa, for example. Does that answer your question?
I guess so, because I'm curious to see like if they were, so say for instance, we were running this machine learning model through uh, a camera in a sense, and you would scan over a bed of flowers, and and again we have 150 versions of these. Would we be able to use this decision tree to be able to tell which flower is which, if it was Certosa or Versicolor or Virginia? Like, and I'm trying to picture that using that type of example. So when it does the decision tree of like which plant this is, it is looking at this particular time, it knows that it had 150 versions already, and the leaf node where it ends, where it makes the final decision, and it's like out of the 50 we've had samples of, it is exactly like this 50, as opposed to if it goes to another flower and it says false, that's why I'm getting confused because it says 50, 50, and 0. And so that's what I'm trying to figure out. The split node and the leaf node, how is it making that decision using value?
Yeah. So the one thing I would say here is this example is much simpler than looking at a camera or anything like that. So we only have two variables in our data set here. We have petal length and we have petal width. If you had all of the pixels of a camera or something like that, it would be a much more complicated decision tree. You would have to be filtering on like certain pixel intensities and stuff. But yeah, the way that this is thresholding is it's picking a specific value for one variable. So this petal length, we're just saying only focus on petal length and then set some threshold on it, and then that separates things out in a certain way. So we're saying at the top we make this decision, and then that splits it into two buckets. 50 of them go over here, the other 100 go over here, and then we continue applying that until we get adequately separated classes.
Okay.
Just
That
a
helps.
quick comment to level set. I'm not sure if this is a question, but so this is still supervised learning. And so in this small example, we have a training set that has 150, it's tabular data. It's 150 rows, 2 columns. That's our training data. And then ultimately, when we do inference, we'll just pass in one sample, which would just be 2 numbers because there's only 2 columns. So I'm not sure if that was clear or not, but I wanted to just maybe clarify that. And then please continue with your question.
No, that helps a lot. That helps me look at it differently. Thank you.
Yeah. So one of the nice things about decision trees is this functions in a similar like simple way that we can interpret. So when we look at this, we can say, oh, I understand anything less than this ends up a setosa, and anything above this petal width ends up a virginica. So the nice thing about decision trees is they're considered white box models. We can directly look at, okay, you're thresholding at this value, so you're changing the decision in a certain way. This is in contrast to like neural networks. Those are considered black box models because it's got all these parameters, and then you say, why is it coming to this conclusion? It's very hard for you to actually figure that out. There's too many parameters for you to directly interpret what's going on. So decision trees are kind of like the gold standard for interpretation. You can also look at linear regression, and then you say, look at all the different coefficients. And in my opinion, decision trees are even more interpretable than that, because if you have a linear regression and you say my coefficient is 0.71, what exactly does that mean? That's kind of difficult to interpret still. Yeah.
So you just mentioned this topic of interpretability, and one can imagine that even today, with all these developments in machine learning, companies are still reluctant to go with machine learning models. They still have rule-based systems. How do you think they can leverage decision tree and similar implementations to augment or to justify the changes they are making over a period of time to their real-based systems? How can both of them operate close to each other to kind of get faster turnaround time or better explainability, interpretability? Any thoughts there?
Yeah, so decision trees are used a lot for interpreting other models as well. So one of the things that you can do is you can train another model and then say, train a decision tree to mimic that. And then you can go look at the decision tree and say, okay, now I have decision boundaries based on what the other model was doing. And then you kind of get an approximation of like, okay, I have this fancy model that's very accurate, but now I need some way to describe what it's actually doing. And so one of the ways that you can do that is you can train a decision tree on top of your other model. So at my last job, I worked with a lot of banks, and that was a very common sticking point for them, where it's like, we want the most accurate modeling possible, but we have regulators that are looking down on us and need certain guarantees about the way our model's behaving. And so there's a lot of interpretability and explainability tricks that people will do in order to get, they try to get the best of both worlds, but it's very difficult. You're typically sacrificing some amount of model performance for interpretability, or vice versa. Like if you're doing a decision tree, you're not getting the most accuracy possible. But yeah, there's a lot of tricks that can be layered on top. So then moving on to the class probabilities. So one of the things that you can do on top of these decision trees, so it typically gives you just a hard output. It says it's this Virginica, it's Setosa, it's something else. But the other thing that you can do is you can look on top of this and then you can say, look at these values that we were just discussing, and then use that as sort of my probability. So the way that I think about this is like we bin the data in various different ways. And then in my training set, I ended up with 49 this and 5 that. So that gives me some sort of estimate of what probability is it that it's these different options. So at this point, we say it's 0% Setosa, because in our training data, we never saw this as one of the possible outcomes. So you can kind of use this as a proxy for probability. So if you have a lot of data, if you don't have a very deep tree, you can probably interpret it decently well. If you have a relatively small data set, if you have very high depth or something like that, and then you end up with tons and tons of different leaf nodes, I probably wouldn't read too much into it. If you end up with something where it's like this random leaf node only saw 7 data points, then I wouldn't really interpret its distribution as probability anymore. So one of the things that I was discussing earlier is like the class probability, you can't interpret it, it doesn't extrapolate at all. So if we look at this plot here, if we extend this out to petal length of 10, for example, we can see by eye there's a trend going upwards where it's probably leaning more Virginica. But the decision tree is so simple that it will just continue to say it's versicolor. And so in the same vein, your probability is not calibrated in any way with like some coefficient saying increase the probability in this direction. So like if we said this bin has 49 of this and 5 of that, going further in the direction isn't going to say, okay, now it's 54 and 0, for example. It's just this entire bucket gets that certain probability, basically. So we've talked about the details of the decision tree, but then how is this actually trained in the background? So this is done using CART. And so the way that this works is it iterates through all of your features and all of the different values, and then it's trying to find the specific feature and split that gives you the lowest impurity. So you have to keep kind of two things in mind. So in theory, we could get maximum purity every time, but that's not very useful. That would be like, imagine we draw a boundary and we just say everything above 6.8 is a Virginica. That's not a very useful boundary because it's only separating a single data point. So we have to balance. We want to capture the many data points, and we also want very high purity. We have sort of a trade-off going here. So that's the gist of what CART is doing, though, is it's saying evaluate every different feature. So in this case, we only have 2, but imagine you have 1,000 or something like that. It's basically going to each feature one at a time and then sweeping through their values and saying, how well can we separate based on a split on these? And so it does that. It finds whatever the purest split is, and then it continues on and tries to find the next split based on that, and it recurses. So it just keeps going deeper and deeper. So one thing to note about this is that it's a greedy algorithm. So in theory, it's just going for whatever is the best at the specific moment. There could be some better tree going a different path, saying I'm going to do a slightly worse split here, but it's going to give me a better split somewhere else. But with decision trees, we just train them greedily. And then the way that most people work around that is you can train with different hyperparameters. You can train it multiple times, and you end up with multiple decision trees, and you can figure out what the best outcome is. And generally, you end up with something that's already good enough. It's not really a matter of like you end up with something that's so suboptimal that if you did a different search, you get a totally different outcome. In general, you'll converge to something relatively similar if you have enough data, if you have enough depth and everything. So I have a little pop quiz question. So if we had unlimited depth tree, so imagine you have a scenario where you can put a tiny little box around every single data point. Is there potentially a scenario where you still don't get a perfect fit? So if anyone wants to take a stab. So if you, I'll repeat the question. So if you have an unlimited depth tree, so the tree can make as many splits as it wants, is there a scenario where it doesn't end up perfectly fitting all of the data?
And we're talking about perfect fitting to the training data, right?
Yeah.
Okay. What first comes to mind is if you're dealing with a small number of variables, you could have multiple points with the same values, like two plants, for instance, that are different species but happen to have the same petal width and length. So you have two overlapping points.
Yeah, exactly. So it's actually common in data to you measure your flowers, and this one's virginica and this one's setosa, but they just happen to have all of the same values. So that's exactly what I was looking for, is sometimes you can have actual overlap of the data where this one was a certain class and this one was another class. And so that's one of those scenarios where your model just can never represent your data. And so that's typically where you want to introduce maybe another variable. So like imagine you have width and length and color or something like that. And then now you have enough freedom to actually represent the relationship, but with just those two variables you couldn't before. Yeah, perfect. So then moving on to computational complexity, the decision trees are extremely fast to compute. So when you're trying to do many predictions, it can happen virtually instantly because all it needs to do is do some basic comparisons when it's going throughout. So if you have two variables or 1,000 variables, it doesn't scale very poorly because it doesn't have to look at all 1,000 variables at a time. It only looks at one. So at the one branch, it's saying, is it above this length for this variable or is it below? And so it's able to just quickly look at individual variables at a time. So at inference, it's extremely fast. It's like instant. Like no matter how many variables you have, it's not going to matter. It will happen very quickly. On the training side, you have to do that process that I was talking about, where you actually go through every variable and then every split. And so you end up with something that scales slightly differently. So this top one is the inference complexity. So this is log 2 of m, which is your number of features, I believe, samples. I'm not sure because this. Okay, I'll believe you for that. Okay. Yeah. Because then you have the training complexity, which is the you have the number of features, and the number of data points also matters because you need to be able to go through all of the features, and then you need to go through all of the splits of the data. So on the training side, it does actually scale with the number of samples that you have. So you have 1,000,000 data points and you have 1,000 features. That means you have to go through every feature 1,000,000 times. So on the training side, you end up with this complexity, which is still not that bad. One of the books that I've been reading recently has been talking a lot about arithmetic intensity in terms of like deep learning. So it's basically the idea of like how much compute are you doing per bit of data. And so for this, it's like virtually zero compute because you're just doing an individual comparison. But So on this side of things, you only really care about the bandwidth that you have. How quickly can you read your data and sweep through things, because you're not really doing any math. You're just doing comparison of values.
Quick comment. So in terms of the amount of compute, you don't need to memorize this. The idea is just to get a sense for it. But here we had numeric values, and so they're saying, assuming that your M samples all have unique values, then we have to try splitting to the left and right of each one of those. To the extent that you have duplicates, then it's not quite so bad. And so then in the extreme is if you have categorical data. So if you have a column that's is student and it's either just true or false, it actually only needs to try one split to say, hey, if I split the trues from the falses, does this give me a really good Gini, or does some other feature give me a better one? So the running time is a little bit better depending on your actual data.
Yeah. So we talked about Gini. There's also this alternative entropy. So entropy is something you'll see in plenty of machine learning and deep learning stuff. It's not really that critical for trees. Most people just use Gini. It is an option that you can swap, but most people just use the default because it doesn't tend to actually make that big of a difference. But if you look at this is a different way of calculating versus the Gini. So you plug your values into this formula instead of Gini, and you end up with a slightly different output. So now moving on to regularization.
Sorry, before you go to the
Yeah.
question online, the book just does binary trees. Can you have more than a two-way split with subnodes?
Yeah, so they mentioned in the book we only typically do binary, but there's also, they mentioned ID3, and there's various other implementations where you can have multiple different leaves per node. But it's not very common, I would say.
Yeah, the other thing that I will mention is that they show the CART algorithm in the book because that was one of the early most successful algorithms. But there are a bunch of different ones. And one of the key things that's nice about trees is that most implementations today allow NAs or nulls in your data because it's just splitting things. And so it can just sort of, it doesn't matter if it's actually numeric value or not. And so it can say, I'll split all the NAs from all the numeric values, or I'll treat the NAs as a super low number, or I'll treat them as a super high number, or whatever. It's not necessarily perfect, but whereas almost all these other algorithms require you to scrub your NAs, you don't actually have to do that for most tree algorithms, which is really convenient.
Yeah. Decision trees are very convenient in that regard. You don't have to worry as much about scaling and cleaning and outliers and all of that stuff. So they're very robust to that. There was a comment online saying like that multi-branch approach can be approximated with just the same splits, just with binary nodes. So that's a good thing to point out. You can basically say, okay, maybe it adds a little bit more depth to your network, but in reality, or to your decision tree, it doesn't actually change the result. You can get the same thing out of binary as well. So going on to regularization, there's tons of different options that you can mess with. I'll show in a second. In Scikit-Learn, there's many options, but the majority of them you don't really have to touch. There's a few key ones that I would say are like the really important ones. So there's max depth. So in the example we saw earlier, this was with max depth 2. And so typically you want to constrain it in some way so you don't end up in the degenerate case of just drawing a box around every single point. So depth is probably the biggest one that I would focus on. Max features is also valuable, so you don't want it fitting on every single feature going down the line until it ends up on a feature that has no predictive power, but maybe is just random noise. the min samples per split. So you don't want your random points to be split up. So if you have something that only has 3 points, you don't really want it split 2 and 1. You're starting to get too specific where it's like not probably the true pattern anymore. Same things with leap nodes. And then this fraction one is saying basically based on a fraction of your data versus fraction or versus just a hard count. So the fraction is saying I have 100 data points. I don't want to split out just 1% of them or something like that. So here's just a plot showing the difference between a non-regularized version and a regularized version. So this one, you can see it starts making that crazy pattern of like, I'm going to draw a tiny little box around this data point, and I'm going to have this weird boundary just like going off into infinity. And so the regularized one gives you a much nicer pattern to look at, and probably better generalization for future predictions. So we've talked about classification now, but then extending this to regression. Regression can function very similarly, but instead of doing Gini, it's doing mean squared error or some other distance metric. And so with this, you can see it's doing the same problem of saying, if this x1 value is less than negative 0.303, it gets a certain squared error between the splits, and its expected value is this. And so you can keep branching and keep getting more and more precise results. So this is what the tree would look like. But then if you look at the decision boundary, you can see it's got a max depth of 2 that they set. And so it's following this parabola pattern. And you can see it's very limited in the number of splits that it's able to do. So it's not really able to follow along this curve. It's just saying, okay, everything here is this, everything here is this, everything here is this. And so if you add more depth to it, you can better approximate the curve. But in general, decision trees aren't great at that kind of thing. So now, in terms of orientation sensitivity, one of the interesting things about decision trees, we talked about, like, you can only go in your orthogonal directions. And so the difficulty with this is you can have this pattern on the left where it's just easily separable, and then you can say just rotate it this way, and all of a sudden it takes a million splits in order to get that same pattern. So you can see just rotating the data ends up just screwing up your decision tree, because all of a sudden it's not able to make a clean split like this. So one of the tricks around this is you can do PCA on top of your data, and it will try to orient things so that it's more easily separable like this. So that's what this plot is showing, is basically you do PCA on top of your data, and then it orients it that in such a way that it's better for your decision tree to learn. So one of the things we mentioned a second ago was that your decision trees are very robust. You don't need to scale them. You don't need to deal with outliers. You don't need to fill in missing values. They're very good for that. But then when you start doing a process like this, where you're saying do PCA, all of a sudden that becomes a problem again. You need to actually deal with those values. So something to keep in mind. So decision trees are considered to have very high variance. So like I was saying, they can theoretically just draw a box around every single point. But also when you rerun it, you can get very different outcomes. So if you shovel your data differently, if you have different hyperparameters, if you give it a different seed, you can end up with a totally different decision tree. So this is a fault of the algorithm, but it also ends up being a benefit in the end. So In the next chapter, what we'll be talking about is ensembling and random forests. And what you can do is you can basically say build mini decision trees, and then their little quirks inside of them will even each other out, and you'll get much smoother decision boundaries. So that's all I have for the doc. I did want to actually go through the notebook if we have time. I'll pause for a second. Any questions on the chapter up to that, and then I'll go through the code.
So Ryan, just one quick comment. So when we say high variance, this is again that bias variance trade-off that people talk about in machine learning. And the variance here is not exactly the same thing as when you learn statistics and you learn like mean, variance, standard deviation. So there may be connections, but I find it easier to just sort of think of it as a completely different concept. Okay. And so the important thing to understand, if you were trying to use just single trees, so we're not moving on to the next chapter yet. Generally speaking, people have problems with that. Okay. So it's not a very popular algorithm as like the final algorithm. We'll see that it's very popular in its use as a building block. And the thing to think about is like last week we talked about in a support vector machine, one of the things you're saying is not all the points are equally important. The ones, if you're doing classification, the ones that are near the other class are super important, and the ones that are far away aren't considered at all. In a decision tree, every point matters again. That is one of the things. And it matters so much that if you just change the petal length on one data point, you could get a completely different tree, you know? And that's what they mean by high variance. It's highly variable. Slight tweaks to your data can have you wind up with a completely different tree. Now, by the way, that doesn't mean that the performance of the tree is going to be much, much worse, but it does mean that the actual tree itself will just be very different. So, so that is kind of a tease to, is there a way in which we can reduce the amount of this? And then the answer will be provided in the next chapter. Can we take advantage of what Ryan was saying, is that it can pretty much be very flexible and find patterns for anything, but can we lower this variance property? And then it turns out, like not exactly a secret here. If you use multiple trees and in some way average them or whatever, then that does seem to help lower this variance problem.
Cool. Thanks, Ed. So I'll run through the code. I won't go in too much detail. I just want to show some of the pieces of it. So in the chapter, this is the code that we started with. So you have your Scikit-Learn, it loads the data set, and then you have your decision tree classifier, and it's learning from these two variables. So if you want to, you can mess with the depth, and then you end up getting a different visualization, potentially. So the original one that they showed only had depth of 2. This is some scikit-learn function that then turns it into a graph that you can look at. So this graph biz will pick it up and then actually make the visualization for you. So this, I expanded it out to have 4 variables or 4 depth instead of 2 depth. And so now we can see it decides to make even more splits. And so you can see we're starting the same, but then at this point, when it terminated on the other ones, it's continuing to go on and say, split it more. So there's no other restrictions on it. So it just keeps doing splits until it gets perfect separation, except for this one, I guess. So one thing I'll note about this is it's a nice thing to look at, but in reality, most data sets you're going to fit on top of it. I've tried this before, and you end up with a graph that's like 60,000 pixels tall and like way too wide, and you just can't even read it. So it's nice to look at, but in reality, you probably won't be making these visualizations. It's just too hard to manage. So here's the code that they used in order to make the various plots. A lot of this code is just going to be plotting. So when you want your probabilities out, they showed us how to do this in theory, but this is how you do this in Scikit-Learn. You say predict prob A, and this will output what was learned during that process. So we see that this was the different bins that things fell in. 49 of them fell on this one, and then 5 of them fell on the other one. And so predict prob A will give us actual probabilities, and predict will tell us just the specific classification is just saying class 1. So if you want more information, you use this option. If you want just a hard classification, then you use that one. Then they did a similar thing, but with the moons data set, and they basically said generate some moon patterns with a certain amount of noise. And then they're trying the same thing with and without a regularized version of the model. And then that's what yielded this plot. So they're measuring the classification performance with some score function. And so this is saying basically the non-regularized version gets this score, the regularized version gets this score. So you can see it went up like 2% because they chose to regularize it. The regression side of things, this is the same plots we were looking at. So you can reveal the thresholds that were picked, and then you can see this is creating the same boundaries that we saw in the book chapter.
Hey Ryan, if you hold on that graph with the parabolas, the yeah. So I think you mentioned this really briefly, but just to reiterate, when you draw a box, in this case, we just see some vertical boxes. The prediction is the same for anywhere in that box. So in this case, when you just look at it by eye, predicting the same exact value, whatever that red line is for any given box, on the far left of the box versus the far right of the box seems to our eye like that's not such a great idea. But that is the limitation of the way decision trees work. And again, don't want to over index on this because people don't use single decision trees by themselves. But there are people who've experimented with, oh, well, why don't I just for each box add a little bit more complexity and like maybe fit a line to it instead of having it just be a constant value. And if you wanted to, there are libraries out there that do that. But in terms of just your understanding, it really is, it's this very flexible tool, but in some ways it's really kind of dumb.
Yeah. Like ideally, instead of saying, okay, everything in this box, you could say, I want some coefficient. So it has a certain slope along with it. So you say, okay, in this box, it's this slope. In this box, is that slope. So you can do stuff like that on top of it and end up with something even more powerful. But in general, decision trees are very powerful. They're just not that intelligent in the way that they do things sometimes. So like in this example, we see it's doing no restrictions. It's just saying little squiggle to hit every single point, versus the more regularized version actually gets the pattern much better. So this is all the same stuff from the book. It's just showing here's the code that actually generated this. So you could see how did they rotate the data in order to make this plot. So they said we have some regular input data, and then we're saying we're going to rotate it with this rotation matrix, and then we'll fit it again, and we'll see what outcome we come to. So that's how we get to this. So this is the same data. It's just been rotated a little bit, and then comes up with entirely different boundaries. So this is the PCA implementation. So this is what I was mentioning earlier. So when you do it this way, you need to do the standard scalar first, because PCA expects your stuff to be normalized in a certain way. So with this, then you get back your original reduction. So you have a decision tree that can make very simple decisions again. Yeah, I think that's it. All right. Any questions on the code?
Did you go ahead? I kind of spaced out for a second. You said somewhere you introduced PCA,
Mhm.
and it looks better here in the graphs. Is that you're talking a little ahead of time, which is not there in this chapter, or what?
So the PCA can be done in order to try to orient your data to make it better learned by the decision tree. So they showed it in the chapter. This is one of the tricks that you can do in order to get cleaner decision trees if your data might be rotated in some way. So in
Okay.
this code, they're showing basically we have this data, we rotated it, and then it becomes very hard to learn. And so if we do PCA on our data, it comes out even cleaner than if we didn't do PCA on it.
Yeah, so for like an extreme example, if your data was just height of people in feet and height of people in inches, it would just be this line with a slope of 12, right? And if you just literally had that data, then the best that a tree could do is have this staircase that has like a million steps to try to do it. There's no way a linear regression could just say, oh, my coefficient's 12, and bam, it follows the whole pattern. So what they're saying is, hypothetically, if you rotated that data so that it was either horizontal or vertical, then the tree could do the same thing. Your data doesn't usually have such a simple thing, but it is important to understand that if you got lucky with that alignment, then you might need a tree that's very shallow, that has low depth, and it actually fits the data really well. And any more than that might be overfitting. But if you happen to have something that requires a diagonal staircase, you might actually need a much higher depth in order to get more or less the exact same pattern, the exact same fit. Okay. And this is one of the reasons why when you're try to do your hyperparameter tuning, people can't tell you up front, like, oh, a good rule of thumb is always use tree depth 3 or tree depth 5, because it really kind of depends on your luck, whether or not you have a lot of diagonal lines that it needs these staircases. Then you're going to need deeper trees and it won't be overfitting. It's just trying to draw a diagonal line.
Okay, cool. Thank you.